Dear students, we rejoined our class today to discuss our next type of rigid body kinetics, that is what is termed as the rotation of a rigid body about a fixed point, which is also known as the fixed axis rotation. As we recall from our study of kinematics, that in this case the rigid body rotates about a fixed point, which is termed as the center of rotation, and the line which is going to the perpendicular to the plane of the rigid body and going through that fixed point is known as the axis of rotation. And in this case the axis is a fixed axis in the sense that the axis does not wobble in the space, so it always remains in the inertially fixed direction. So that is why it is called the rotation about a fixed point, and it is also termed as the fixed axis rotation. So in this case, that the center of rotation can be any arbitrary point, or it can be, in this case we will call that rotation as non-centroidal rotation, and there may be a case in which the rigid body is say is found to be rotating about its own center of mass. In that case the center of mass itself actually plays the role of center of fixed center of rotation, and in that case we call that rotation as to be the centroidal rotational motion of the rigid body. So in this case of we know that in the case of this fixed axis rotation, all the different points of the rigid body will be appearing to move along the set of concentric circles, for which the center of those circles will be the center of rotation. In case of non-centroidal rotation, that is a non-centroidal point, and in case of centroidal rotation it will be the center of mass of the body, and the different radii for those different circles will be the corresponding distance of that point from that fixed center of rotation. So in this case, let us consider that this is our rigid body, and here we assume that the body is undergoing non-centroidal rotation, in the sense that the body is having the center of rotation as point O, which is not the center of mass of the body. And let us suppose that the C is the center of mass of this rigid body. And in the free body diagram, let us show this is the free body diagram. Free body diagram means that we need to show all possible external forces which are acting on the body. So that possible force list, we may have the external forces, like say this force, we may call it as F1. We may call this force as the force F1. Then we may call this force as F2. Then we can go and saying call that as Fn. And these are all your external forces, and these pink vectors, they indicate the reaction support, or the reactions as provided by the fixed axis or the fixed center of rotation, because we see that the body will be rotating about this point, so it means that at this point at least the body will be hinged. So these will be therefore the the reaction forces which will appear at the center of rotation because of its hardware and all. So these forces we can call it as ROX and ROI. Say in this case we take this arbitrarily, this horizontal direction we call it as the x-axis, and the vertical direction we take it as the y-axis. Now we may consider the center of mass of this body to be here at point C, which is at a distance of r bar from this point, and we can also designate the another set of axes which we call as the normal tangent coordinate axis. In this case the normal direction will be the direction, because in this case when it is non-centroidal rotation, the center of mass will be appearing to moving along a circle whose center will be the point O and whose radius will be this r bar. So this distance, I mean to say along the direction of C to O, this normal axis is directed. So this normal axis, although it has not been properly represented in this figure, but we need to understand that this n axis basically the line along the direction C to O. So the ON axis is actually in CO direction. Okay, and we can have the tangential direction in this way, or we can have the tangential direction in this direction as well. That means what I mean to say is that let us take this this tangential line. Let us take this tangential line here. So this is our the tangential line. We can take it like that. Sorry, we can take this line. Okay, let us draw it here afresh. So this is your, this is representing the tangential direction. We show it in this direction. It is because we assume that our this is our t-axis. So we call this as the normal direction and this is the tangential direction, because we say that omega is the instantaneous angular velocity of this body and alpha is the instantaneous angular acceleration of the body, in which case we know that alpha is equal to the magnitude derivative of this angular velocity with respect to time. So we call this as alpha equal to omega dot, and we take both these vectors in the anti-clockwise sense as the positive ones. So I repeat, therefore the normal axis is taken along the direction C to O and the tangential axis will be its perpendicular. So it is an alternative set of descriptions. We may have this xy coordinate as well, we may have the normal tangent coordinate axis. Suppose if we take this as the normal tangent coordinate axis, then we know from our knowledge of if this is the free body diagram, then we know that the center of mass is having two accelerations. One will be along the normal direction, that is omega square into r bar, and another will be the tangential direction, which will be we see that which we can write it as alpha or omega dot into r bar. So this will be the components of accelerations. So the corresponding forces will be m omega square r bar and it will be m r bar alpha. But you know that the body, because it is rotating with an angular acceleration of alpha, we see that the body will have the it will have the resultant moment about the center of mass, and this will come from the definition of that the torque, the net moment, external moment which is acting on the body, that must be equal to h bar relative dot, if you remember that. So that h bar relative dot can be simplified to this factor called I bar alpha, where I bar is termed as the mass moment of inertia of this rigid body about an axis which is passing through the centroid or the center of mass and is perpendicular to this plane of rotation. We will see how this I bar will come into picture in the form of our derivations of equations of motion. So first thing, that is pretty obvious that we can apply here the generalized second law of motion, Newton's generalized second law of motion, which states that the sum of all the external forces which is acting on the body on a system of particles, and we know that from our knowledge of system of particles that we can easily extend that system of particles to the concept of what is termed as the rigid body. So therefore we can have this and we can write this first equation which is nothing but what is also termed as generalized Newton's second law of motion. So we term this as generalized Newton's second law. Second law of motion. So that is our first thing that we will be having here. So we will be having this generalized second law of motion. So from this generalized second law of motion, we can say summation F bar. This represents the sum of all the external forces as disclosed by this free body diagram, and this is its equivalent kinetic diagram, must be equal to m into a bar bar. Remember, this a bar bar is actually the acceleration vector of the center of mass, which is actually either can be written as, say, a bar x and a bar y, or it can be expressed as a bar n and a bar t. So either we can express the Newton's generalized second law in along this x-axis and y-axis by these two sets of equations, or alternatively I can also express this in terms of this normal tangent coordinate axis. And if we do the latter part, so then it will become summation Fn equal to m omega square r bar, and summation Ft, that becomes m r bar alpha, or which we can write it as m r bar omega dot. So therefore these two equations 1 and 2, they represent what is termed as the scalar, they are the scalar versions of generalized Newton's second law of motion. So this is pretty clear because we already know it. Now regarding the moment, because these forces, as I have already mentioned when we discussed the kinetics for translational motion of a rigid body, we told that these external forces are basically acting at the different locations on the body. So since these forces are acting at the different locations on the body, so they have a planar distribution, so to say. So as a result, we must be having some effect of the moment. So we know from our knowledge of system of particles that we can take the moment of all these external forces with respect to the center of mass. And if we take this with respect to the center of mass, then I can write that this should be equal to h bar relative dot, or hc bar relative dot. We can take this h here, this h represents the angular momentum of this body about the center of mass. So I can write this as summation mc equal to ddt of integration r square omega dm, where the r is what? Let us consider that this is an arbitrary mass particle belonging to the body. And let us also suppose that this mass particle which is arbitrary, is at a distance of, r from the center of mass. So this distance is r, and here we have this small mass particle which we can write it as dm. Now because of this, the relative velocity of this mass particle with respect to the center of mass will be equal to omega into r, and the linear relative momentum, right, that will be equal to how much? That will be omega r into dm. So what will be the angular momentum of this small mass about this center of mass, which is the relative, as well as it should be absolute, because we know with respect to the center of mass, the relative angular momentum and absolute angular momentum are basically the same. So I can call this as the relative angular momentum, and can say that the relative angular momentum will be, for this small mass, it will be it will be omega r square dm, because we know that omega r dm is the relative linear momentum, and its moment about the center of mass is obviously omega into r squared dm. So if we now perform this, if we can integrate it, because you know all these masses are uniformly distributed within the domain of this body, so I can integrate it and can write that it is integration r square omega dm, and we can differentiate this to find out this quantity. Now in this equation, everything is with respect to this integration, so to say, with respect to this integration, I can take this omega out of this outside of this integration, and can write this as omega into integration r square dm. Let us first simplify this bracket first, and then it will become omega into I, where I represents this integration. That means integration r square dm. So it will be basically ddt of omega I, right? Because if you take this omega outside of this integral, so it becomes omega into I bar, so to say, because this is the mass moment of inertia of this entire body about an axis which is passing through the center of mass of the body. So that we can therefore say it is I bar. So it is ddt of omega into I bar. Now we need to remember the fact that this coordinate axis, so this coordinate axis, I mean to say this normal tangent coordinate axis, suppose in this case, will be actually attached to this rigid body at point C. So either it will be the xy coordinate or the normal tangent coordinate, whatever we are going to deal with, they will be either attached to this rigid body at point C or the center of mass for calculating the moment, or it will be attached to the point O. About that I will come later, since we are dealing with the moment about point C. So let us first focus on to it. So what we are doing, we are taking this coordinate axis either xy or nt, right? So this coordinate axis are actually fitted to the point C rigidly to this body. So when we do that, we see that these coordinates will also rotate with this rigid body, with this angular velocity, with this angular acceleration. So it is pretty clear that this I bar will be remaining the same, because you are also rotating, your coordinate axes are also rotating with respect to the body. So it means that if these are actually the inertially fixed one, so what I would say, every time with respect to the center of mass, the orientation of the body would change. But if I allow the axis to rotate with the body fitted with it at center of mass, we will see that the mass distribution of the body with respect to the center of mass will remain invariant with respect to time. So it means that although I write this equation as ddt of omega into I bar, I can take that I bar independent of time, and the differentiation will be only done on omega. So ultimately it will be omega dot into I bar. So if I call this as I bar and I write this is omega bar dot I bar, or it is I bar into alpha. So the takeaway point or the bottom line of this story is that this coordinate axis need to be fixed to this body at center of mass. For this case, for the present case, when we are going to take the moment of all these, with respect to the point C. So we need to fix this coordinate axis with to this body, to the center of mass of this body, and allow the axis to rotate with the present angular velocity and angular acceleration of the body. So here we assume the rigid body to be the slab-like body. We also assume that this rigid body is slab-like in the sense that it is like a plate-like body. So I bar will be termed as the mass moment of inertia about an axis perpendicular to the plane of the body and coinciding with the axis of rotation. Now I bar can be written as this, integration r square dm, and it is also written as m k bar square, where k bar will be termed as the radius of gyration about the center of mass. Now, two things are there. First of all, regarding the assumption of our coordinate axis, that it needs to be body fitted. As far as this moment equation is concerned, we don't have any problem so far as the force equations are concerned. So we don't mention anything about the coordinate axis, whether it is body fitted or it is not body fitted, it doesn't matter for the force equation. However, for the moment equation, it needs to be specified how we are attaching the coordinate reference frame with respect to the body. So that is number one assumption. Number two assumption is regarding the geometry of the body. Here we have casually mentioned it, that the body is a slab-like or a plate-like body. The actual significance of this statement will be pretty clear to you when we will be going to study the more elaborate kinetics of rigid body with reference to its three-dimensional motion. There we will learn the full significance of this mass moment of inertia terms. However, we are not actually right now embarking onto that particular study. For us, it will be actually the body which will be considered as a slab-like body, or either it can be considered as a slab-like body, or even if the body is not a slab-like or a plate-like body, it may be an extended body like a cylinder, and the rotation should be taking place about its own axis of centroidal axis. If this situation permits, then only we will be able to write this equation. So for us, it is sufficient to remember two things. First of all, regarding our coordinate axis fixation. Secondly, about the geometry of the body. For us, more or less all bodies will be slab-like or plate-like body. However, there is an exception to it. We may have an extended body like a cylinder rotating about its own geometric axis. So in that case also we can use this equation. Now this is one alternative description of your moment equation. Now you need to remember or need to recall your analysis of the system of mass particles. We know that this sort of equation is also applicable if the moment and the angular momentum, corresponding angular momentum, these two are calculated with respect to the fixed point. Now looking at our present problem, we find that we have a fixed point, and that fixed point is actually the center of rotation of this body. So either we are going to write our moment equation here with respect to the center of mass, or we can go and write this moment equation with respect to this point O, which is treated as to be inertially fixed point. So therefore, we take the second option, that we can go and write the moment equation now with respect to the point O, and accordingly all the coordinate axes for writing this moment equation will be now shifted or attached rigidly to the body at point O. So again, if you describe the first, if you come in the logical manner, the way that we have shown here, we will be able to prove here that the above equation can be expressed is like this, that it is IO omega dot or IO alpha or MKO square alpha, where this time now this IO represents the mass moment of inertia of this entire body, about an axis which is passing through the point O and is perpendicular to this body. So that IO will be the mass moment of inertia of the body about point O. So therefore, students, here we have two alternatives for writing our moment equation, which alternative we will be going to write depends upon the problem at our hand and the situation at our hand. But we have two alternatives. Either we can write our moment equation with respect to the point C, the center of mass, that is one alternative. And another alternative is, of course, to write the moment equation with respect to this fixed point of rotation. Now, the advantage of writing the moment equation with respect to point O is to eliminate these two reaction forces automatically, because in many instances these become our unwanted unknowns. So on many circumstances we may have to write our moment equation with respect to the point O in order to naturally eliminate these two unwanted unknown forces. So we have therefore our free body diagram shown here and corresponding its equivalent kinetic diagram shown here. Of course, here the kinetic diagram is shown when we are going to write everything with respect to our center of mass, or we can write it with respect to the point O also. So therefore, this is one alternative that we have. Now, for writing this moment equation about this fixed point O or the center of rotation, we can proceed as summation MO, that represents the sum of the moment of all external forces about point O. So either I can calculate this IO by the equation IO is equal to integration, we can write it like that, it is integration r square dm, where r is the distance of the differential mass dm from the fixed point O. That distance we can represent it by r and can write this mass moment of inertia. We can express this mass moment of inertia in this way. That is one thing. Now here, of course, r represents the distance of that arbitrary mass point from the point O instead of the center of mass, as we have shown earlier. So that is, this way I can calculate our IU. That is one alternative. Another alternative is that we can employ what is called as the parallel axis theorem. We can employ the parallel axis theorem between the centroidal axis and a non-centroidal axis. In this case, the centroidal axis mass moment of inertia is I bar, and if I try to shift it from the centroidal axis C to the non-centroidal axis, to the non-centroidal point O, then I need to take care of this distance between C and O, which we have mentioned it to be equal to R bar. So I can say that IO is equal to IC or I bar plus M into R bar square. So IO can also be expressed by applying the parallel axis theorem. We can write that it is I bar plus M into R bar square. We can write it like that. So that into alpha, so we can ultimately write it in this manner. So either we will be going to express our mass moment of inertia in this integral this way, or if we know the mass moment of inertia about the center of mass of the body, then we can employ the parallel axis theorem to write the mass moment of inertia of the body with respect to the axis going through the point O. So whatever be our case, we have altogether three equations at our disposal. One will be two force equations and one will be the moment equation. That moment equation will be either written with respect to the center of mass, or it will be written with respect to the fixed center of rotation. So either way I can represent the third equation. So altogether we have three scalar equations at our hand, and we can therefore solve maximum again three number of unknown quantities. Now this is one kind of the approach. Then we have an alternative formulation also. Let us now come and discuss this alternative formulation. So again we represent our original figure of the free body diagram and the coordinate axis. Again we need to just revise our coordinate axis, this t direction. Let us say this is our t direction. This is our t axis. Let us call this is our t axis. Let us say this is our t axis. We write this is t, and we know that this I can equivalent kinetic diagram when we had written with respect to the center of mass. These were the cases m omega square r bar and m r bar alpha. These are the resultant components of all these forces along the normal axis and along the tangential axis, and we have this I bar alpha. So 1, 2, 3, these three things are there at point C. Now what we do, we bring all these forces to some other point. Let's call this point P, which is at a distance away from the center of mass, also away from the point O, and we bring all these forces, instead of acting at C, we bring them at P. So you see, this force is actually shifted along its line of action, and following the principle of transmissibility of forces, which is valid for a rigid body, we see that this shifting is actually a legal shifting. However, if I take this force from this present location over here, m r bar alpha, since no force is there, we see this m r bar alpha needs to be counterbalanced with a negative force vector, which is acting this way. So this pink vector and this green vector will constitute a couple, correct? And this couple will be looking at the front of this figure. This couple will act in the clockwise direction. So if we take all these forces and couples from point C to point P, correct, from point C to point P, then at point P we will be having three things. One is this m omega square r bar, another is m r bar alpha undiminished, same, and then here we will be having a couple, the resultant couple, and the magnitude of that resultant couple will be, of course, it will be I bar alpha minus it is m r bar into, if we take this distance Cp as A, then it will be m r bar into alpha. That means taking common alpha, I say that it will be I bar minus m r bar into A. That will be the couple that we will be having if we bring all these forces from and couples from their present location of the center of mass to this arbitrary point P, which lies along this line OC, right? Which lies along this line OC, and it is away from C and O, correct? So we see that this is the situation that we have. Now I can choose this distance A, because I have taken this point A as arbitrary here. I can choose this distance A in such a manner that this becomes equal to 0. That means this I bar minus m r bar into A is equal to 0. Or in other words, we can say that the point A, that becomes equal to I bar divided by m r bar. That point A can be chosen in that manner. So if we take this, simplify this, then remembering that I bar is equal to, can also be written as in terms of the radius of gyration, centroidal radius of gyration, we can write this to be equal to m k bar square divided by m r bar. That mm gets cancelled out, and we have this acceleration this distance A can be written as k bar square divided by r bar, where the distance cm is taken as Cp distance is taken as A. So that where we choose this A in this manner, the net moment will be 0, and we will be getting then the following equivalence. Now you see the following equivalence we will be getting. Again, we will try to edit the tangential axis. We took the tangential axis in this direction, so Let us first edit it. This is the tangential axis, and we see that this becomes equal to, it was there here with respect to the center of mass, and then we decided that we need to shift all of them to the point P, where the Cp distance that will be calculated as k bar square by r bar, and in that case we will be having only the two forces, and there will be no couple will be present here. That means the resultant of all these forces and moments which are acting on this rigid body, as shown in this free body diagram, is finally becoming equivalent to a simple resultant consisting of the components m omega square r bar along the normal direction and the component m r bar omega dot, which is known as the tangential component of the force, and we need to place them at a special point P, which is at a distance of a from the center of mass, and that a is actually being given by this particular equation. We call this point P, the special point, we call this point P as the center of percussion. So this point P is basically termed as the center of percussion, and we therefore see from here that the resultant of all external forces acting on a body rotating about a fixed point always passes through the center of percussion, and sum of the momenta of all external forces, obviously, since you see here that since your entire system's resultant is passing through the point P, so it is obvious that if you take this point P here, if you consider this point P here, which will be along this line OCP, it should be collinear, OC and P, these 3 points must be lying on a line, and in this order, that is the hinge, this is the center of mass, and then we will be having the center of percussion. So if I now physically locate the center of percussion and take this point here and take this point here, we note that if we take the moment of all these external forces about this point P, obviously because these two forces are passing through point P, so their moment will be 0. So it means that the moment of all these external forces and moments as shown by the free body diagram about this center of percussion, this must be equal to 0 because your resultant is passing through that, and this follows from the principle of what is known as the extended principle of theorem of Varignon, or Varignon's theorem, generalized Varignon's theorem of moment. So sometimes, you know, the bodies are found to be rotating about its center of mass, and in that case, if we consider that the entire body is rotating about the center of mass, definitely we will not be having any centroidal components of accelerations. So your moment equation will remain unchanged, but the force equation will ultimately becoming equal to 0. And since your forces are 0, what I mean to say that these forces are 0 because the center of mass is immovable, there is no question of center of percussion here that is present when a rigid body is rotating about its own center of mass. So the center of percussion becomes relevant when a rigid body is undergoing non-centroidal fixed axis rotation. In that case only we find that in this case the center of percussion will become a pertinent issue. Otherwise, you know, the centroidal rotation, we don't have anything. Now, after going through this theory, so before we go for the discussing the example, let me just quickly recapitulate what we learned in the theory window of our present discussion. We see that we have again, you know, the rotation, fixed axis rotation, either it will be non-centroidal or it will be centroidal. If it is a non-centroidal rotation, we have two force equations as usual, representing the the taking care of the acceleration components of the center of mass of the body, because the center of mass will be now rotating along an imaginary circle about the center of rotation of the rigid body, and the radius will be the distance between them. So because of that motion of the center of mass, it will have some acceleration, and we know that the sum of all the forces, external forces acting on the rigid body as disclosed by its free body diagram, they must be equal to that mass into that corresponding acceleration of the center of mass along the respective coordinate axis. That is the first thing that we need to understand. Secondly, we need to consider the moment, and while considering the moment, we need to remember that we need to fix our coordinate axis. Say if we decided to write the moment equation with respect to the center of mass, then we need to fix our coordinate axis at the center of mass and write our moment equation to make the mass moment of inertia term invariant with respect to time. Otherwise, we will be having a very complicated situation where your mass moment of inertia will also change with respect to time. So that is one alternative, that we are going to write our moment equation with respect to the center of mass. And another alternative is that we can either write this equation with respect to a fixed point, which is in this case as the fixed axis of rotation. So that is one alternative we are having. And finally, we see that if the body is undergoing non-centroidal rotation, then we can have the concept of what is termed as the center of percussion, which is a special point on the body, and that through that point actually we could identify that through this point actually the resultant of all these forces is basically passing. So we can therefore consider, then if we decide to take the moment of all these forces, external forces and moments which are acting on the rigid body as shown in the free body diagram, about that point center of percussion, then we don't need any mass moment of inertia, because the net moment of all these external forces and moments about the center of percussion will be simply equal to 0. So with this background in our mind, let us now go and explain our applications of this particular kinetics with the help of the following examples. So this is first example that we are going to consider. This is example 1 from the book of Merriam and Craig, and this is problem number 6 by 36, where we show that we have a car. Here it is a car, and we have the automotive dynamometer is able to simulate the road conditions for an acceleration of 0.5 g for the loaded pickup truck with a gross weight of 5,200 pounds. And this is what is termed as this dynamometer. This is the dynamometer, which is a a ring which is able to rotate with respect to a fixed axis going through the point O and perpendicular to the plane of this figure. Now, what we need to see that calculate the required moment of inertia of the dynamometer. That means we need to find out the required mass moment of inertia of this dynamometer about the center O, assuming that the drum freely turns during the acceleration phase of the test. So this is the acceleration. You see this car, it is being, there is a chain which is attaching to this car and lock it with the ground, and this is also another chain which is coming and locking it with respect to the ground. And this dynamometer, when it is rotating, we see that there is an assembly. We can show it like that. Say you have a small tire and you have that bigger dynamometer which is there. These two things are having this point of contact, and this dynamometer is seen to rotate in the clockwise direction. So this is along which it is seen to rotate when looked from the front. And then this wheel actually, it will try to rotate then, in the anti-clockwise direction. So this will be therefore the sense of the angular velocity of this wheel. This is the small wheel that we are having. This will be the sense of angular velocity, as well as it will be the sense of angular acceleration, because if this arrow represents the angular acceleration, then this arrow will represent the angular acceleration of the wheel. So if this is omega, it must be having some omega dash. If this is having an alpha, then this must be having this alpha dash, and we will be having a definite relationship between this omega and omega dash and alpha dash, about which we will discuss little later. So what is the thing? First we need to draw the free body diagram of this dynamometer. So this is the dynamometer free body diagram. It is shown here. This is your omega, as we have shown. This is omega, this is omega dot, which is also, this is also written as alpha. So we see that these will be your bearing reactions, which is coming from the axis of rotation. So these are your axis of rotation reactions at point O. And then this is the contact point where the dynamometer is making contact with the wheel. This is the point where it is making this contact. We take this point as point P. Let us call this point as point P. And at this point we have your forces, which is NA, the normal reaction, and this is F, that is the friction force. Now, how we ensure that the friction force is acting towards right? It is because that, this dynamometer is basically what it does. If you look at the statement, it is simulating the road conditions. This is important. It is simulating the road. This dynamometer is basically simulating the road condition. And the road condition is that this wheel, will have this friction force. This is the friction force. This wheel will be subjected to this friction force, which will be actually, in reality, it will be the friction force offered by the ground on the wheel. So this friction force is actually providing the acceleration of the car, which is in this direction. So this is the direction of the acceleration, and this acceleration of the car is actually being provided by this friction force, which acts between the tire and the road in a real automobile which is moving on the road. So had there been no friction between the tire and the road, say for example in a very slippery road or on ice, the car will not be able to accelerate. So if it is at zero speed initially at rest, the car will remain at rest because the tire will simply slip on the surface, and it will not be able to move forward. So as a result, you see, therefore, since the wheel must have the friction force in this direction towards left, so on the dynamometer, the direction of the friction force must be towards right. And the net effect of the whole thing is equal to this I bar alpha, because we are writing it with respect to the point O, and we can say that it is equal to I bar alpha, where I bar is the mass moment of inertia of the dynamometer through and about an axis passing through the point O. So therefore, you see that these are your unwanted unknowns, and this is the case of centroidal rotation. So we don't have any acceleration of the center of mass. So it is therefore simple to see that it is basically the forces are in static equilibrium. That is number one. Number two, that we can take coolly the moment of all these forces with respect to point O to see that actually the F into RD, where RD is the radius of the dynamometer, should be equal to I bar into alpha D, where alpha D is the angular acceleration of the dynamometer. Okay. So I bar thus can be written by this. So this is our equation. In fact, our objective is of course to determine the value of this I bar. Now we now move on to the free body diagram of the car, and if we look at the free body diagram of the car, it looks like this. So you see, this will be the two chains with which the car is being attached with the ground. So if we unlock these two chains here, the tension T1 and T2 will be released here like this, and actually these two tensions must be we see that these two tensions must be equal. So if this is T1, then this must also be equal to T1. So let's say this is also equal to T1. And we have these normal reactions offered by the ground on the wheels, and we have this friction force, and together we see that the car is having a forward acceleration which is equal to 0.5 g. So it must be equivalent to this one, which is the equivalent kinetic diagram. So now I apply the equation summation F equal to m into A, and we just write, putting the numericals, the values, because A is known to be equal to 0.5 g. So we see that the force turns out to be 2600 pound. So that will be our value of this force, which is, the W, the weight of the car was basically equal to 5,200 pound. So half of that, because your A is 0.5 g, so half of that, the force value turns out to be 2600 pound. Now we come and look at the kinematics of the dynamometer and the wheel. So you see, again we have shown here, this is omega d, the angular velocity of the dynamometer. This is alpha d, angular acceleration of the dynamometer. This is alpha wheel, the angular acceleration of the wheel, and this is omega w, that is actually the omega w represents the angular velocity of this wheel. Now this is the point of contact, and this point of contact P, let's say we call it P. So here we see that our velocity and all, and the tangential velocity or the tangential acceleration, because it represents a no slip point. So the tangential acceleration, right, this on the wheel, on the dynamometer, the tangential acceleration of the point P will be equal to this alpha d into RD, and on the wheel the tangential acceleration will be equal to this, that means alpha wheel into RW. So since it is representing the point of no slip, these two must be same. So as a result, we can find from here that alpha d and alpha w into RW, that is basically equal to A. We know this A must be equal to RW into alpha w, correct? We know it from our no slip theory. So if that is true, then this we can write it as A, and we can take this to be equal to 0.5 g. So I substitute this, put these radius values and all these data are known to us. So accordingly we will be able to find out what will be the angular acceleration of the dynamometer. So once this angular acceleration of the dynamometer is known, we come and substitute it into this equation, because you remember we have already calculated what is the friction force, and we have seen that the friction force is equal to 2600 pound. Only thing here is unknown is this dynamometer's angular acceleration, which also we have been able to find here. So on substituting all into this equation, we find that this will be our I bar, that is going to be the required mass moment of inertia of the dynamometer. Look at the peculiar unit, because here we have used the gravitational unit instead of absolute unit. So mass becomes a derived unit, and as a result you have this peculiar unit for mass moment of inertia of the car, of the dynamometer. Sorry, about the point, thus about the axis passing through the center of mass of the dynamometer. So this is the thing that we are getting. So that is going to be my answer. So this is going to be my answer in this case. So students, now I hope that you have understood this example. This is a good example which is showing a practical application of our basic concept. Now we move on to another example. This is called example 2. This is slightly difficult problem as marked by the Merriam. So let's take this problem, analyze the feature in this case. So this is the figure which is being shown. It is representing a uniform rectangular block, correct? And it is released from the condition of rest with theta essentially 0. That means when the block was basically in the vertical direction, correct? So at that point, we release this block essentially from the condition of rest. And about the center A of its lower face on the fixed corner. And it pivots in the vertical plane about the center A of its lower face. So this is the lower face and its center. That means this is the point A about which this the block is getting pivoted. So as if there is some hinge point here, right? And with respect to this hinge, the entire rectangular block falls down. Now, if the block is observed to slip, but since it is not hinged, so it means it is actually a free point of contact between them. And it is noted that the block is observed to slip. So it tends to slip over the surface of the table when theta becomes equal to 30 degree. So find the coefficient of static friction between the block and the corner. So that is our first part of the of our query. And the second part is that if the bottom face of the block is notched, it is notched so that it cannot slip, or suppose it is being hinged, find the angle theta at which the contact between the block and the corner, if it is not hinged, since it is not hinged, so we need to find out the angle theta at which the contact between the block and the corner ceases. So we'll come to this, address this part little later. So first we take up our issue where we see that this block is seen to slip over this edge of the surface when theta reaches to be 30 degree. So let's see, this is our free body diagram when the block has rotated by an arbitrary angle theta from its the initial line. At this point, let us see the free body diagram. So what we will be having, the weight, of course. Now the weight will be divided into its two components, one along this direction, which is W sine theta, and another along this direction, W cos theta. We take these directions as x-axis and y-axis respectively. So accordingly, you see that this will be going to be equivalent to, now your center of mass is here. This is where your center of mass is. So it is tending to rotate about this point A, whose distance and the radius is equal to AC. That means half the length of this block. So I can see that it is equal to W by G into L by 2 if I call this length as L and if I call this as B. So then it is W by G into L by 2 theta dot square is the normal. This is the normal acceleration times mass, and this is L by 2 theta double dot is the tangential acceleration, and that times mass. So these two will be therefore the resultant of all the forces, and of course these are your reaction forces at point A. Since the block is trying to have a tendency to slip in this direction, so naturally the friction will be acting in the upward direction. So there is no ambiguity regarding the sense of the friction force which is acting at point A, and this is I bar theta double dot. So with this, again we note that this is where we are having some unwanted unknowns. So what we do first, we take the moment of all the forces and write the moment equation with respect to A. But before that, we write our force equations stating that it is W cos theta minus the normal reaction Na. This must be equal to W by G L by 2 theta dot square, and summation Fy, that means the force along this direction, is written like this, that it is ma bar y, it is equal to ma bar y, it is equal to w sine theta minus Fa equal to w by g into L by 2 into theta double dot. So these are your two force equations, and the moment equation will be written with respect to the point A here, and we write this is going to be our moment equation. So it is written like this, it is I theta double dot, because we need to write the mass moment of inertia about point A, and this case we can take parallel axis theorem and can write it is I bar theta double dot into m w by g into this distance, that means L by 2 square whole square into theta double dot. So we can say this is I bar plus w by g into L square by 4 into theta double dot. Now since we see that this moment about point A is nothing but w sine theta into L by 2, correct? So this moment is w sine theta L by 2, and this is equal to, I can take this w by g common, because we know for rectangular block I bar, that means the mass moment of inertia of this rectangular block about an axis which is passing through the center of mass of this block and perpendicular to this rectangle face is basically being given by m by 12. It is m by 12 into L square plus b square, and we have this is L square by 4. So if we simplify it algebraically, we can write this side, you see w getting cancelled, we can write this side that it is L square by 3, because L square by 12 plus L square by 4 will ultimately make it to be L square by 3. So L square by 3 plus b square by 12 into theta double dot is equal to g into your L by 2 into sine theta. So we can finally express, putting all these numericals and taking care of the appropriate units, we can take from this equation theta double dot turns out to be something like this. Now we can write theta double dot as theta dot d theta dot d theta. So ultimately then this would represent a differential equation, and I can say that it is theta dot d theta dot is equal to 27.67 sine theta. So now if we integrate this equation, you remember it was mentioned that the system has been released from the condition of rest when essentially theta is equal to 0. So therefore I integrate it between these two limits, 0 to an arbitrary angular velocity theta dot, and correspondingly here, let us say the 30 degree, okay, the angle is taken 30 degree because at that point of time it is found to slip, so we take up to that. So theta dot will be the angular velocity corresponding to the fact that when theta becomes equal to 30 degree. So this will be our integration, and accordingly we find that theta dot square is turning out to be as 7.414 second to the power minus 4. So that is going to be my second to the power minus 4, not, it will be second to the power minus 2. So we can write this, it will be second to the power minus 2. So we see this is theta dot square, 7.414 second to the power minus 2. And exactly at theta equal to 30 degree, therefore we see if we take here, come to this equation, so if we take this equation and put theta equal to 30 degree, then theta double dot will be half of the 27.67, and it turns out to be 13.835 radian per second square. So once I know theta dot square and theta double dot, we can go back to our force equations. You remember the equation from 1 and 2, we have NA and FA present ready for us. So from equation 1 and 2, we can find the value of NA in this expression and put all these numericals to take this is the value for NA, and exactly in the similar manner from equation 2, I can write FA and find out the numerical value of FA corresponding to theta equal to 30 degree, for which theta double dot is 13.835 radian per second square and theta dot square is basically 7.414 second to the power minus 2. So once we find this is FA and NA, then it is pretty obvious that we can take the ratio of these two and find out what is the coefficient of friction. That must be, this coefficient of friction must be there to ascertain that the block will slip at theta equal to 30 degree. So our coefficient of friction has to be equal to, this is the coefficient of friction that we must have at that point. Now, if the coefficient of friction is greater than, actual coefficient of friction is greater than this, then of course it will not slip at theta equal to 30 degree. So to slip, therefore, our mu must be equal to 0.211 to ensure that it will slip at theta equal to 30 degree. So that is our first requirement, that we need to, from this data, that when it is slipping, what is the coefficient of static friction between the block and the corner? We can find out that static friction coefficient. Now, if the bottom face of the block, now come to the second part of the problem. If the bottom face of the block is notched so that it cannot slip, find the angle theta at which the contact between the block and the corner ceases. So that is our second part of the problem. So if we come to the second part of the problem, let us come and notice here. We note that in this case our NA must be equal to 0. And you know that what is the value of NA? The value of NA, you see here, is W by G into L by 2 theta dot square, W cos theta minus W by G into L by 2 theta dot square. Now, since it is losing contact at point A, so essentially it means that the value of NA must be 0. So it means therefore that this W cos theta and this W by G L by 2 theta dot square, they must be equal. So I can therefore say that theta dot square is basically equal to twice G by L into cos theta. So that is what we are getting. Now what we have been asked to find out is the angle theta at which the contact between them. So we need to find at which this contact will be that this normal reaction will simply becomes equal to 0. So we find therefore that our theta dot square, correct, theta dot square, we can write from this equation that NA is equal to this. So NA must be equal to W cos theta, and we can write this is this value. I think we have made a mistake because theta dot square, I think we have made a mistake here, because the theta dot square value that we have employed, that is equal to for 30 degree, but it is not for 30 degree case. So essentially what we have, let us solve this problem here. I think that was a mistake that we have committed, employing that theta dot square value. We note that this NA must be equal to 0. So NA 0 means we have, let me just introduce a fresh page here, page after. So we note that this is our basic equation. Let me take this equation in our hand here in this new page like this. So let me just copy this equation here from here and paste it in the next page. So you see this is W cos theta minus NA equal to this. Now at this point we note that here we also I require the equation which we saw here, that is this equation. Let us go down and find this equation, that is theta double dot is equal to 27.67 sine theta. So let me go and take this equation as well. So we have theta double dot, we can write it here. We have found this theta double dot is equal to 27.67 sine theta. Okay. Now, at the case when Na is, the point is losing contact at point A, so definitely we see that Na is equal to 0. So it essentially means that your W cos theta, this must be equal to W by G into L by 2 theta dot square. So you have this equation. So it means from here that this W getting cancelled, we can say that theta dot square turns out to be as, this is 2 by L into cos theta. Now putting the numericals, you remember that we had considered here the value of L. The value of L was taken as how much, that is mentioned, numerical value of L is 5 by 3 feet. So I just put this value of L 5 by 3 feet, and this is L is 5 by 3, so it means it is 6 by 5 cos theta. So that is the theta dot square that we get. And now I take this equation, and integrate this equation like this. We write that this theta double dot can also be written as theta dot d theta dot d theta. So it means therefore we can write this equation as theta dot d theta dot, that is equal to 27.67 sine theta into d theta. So if you integrate it between the say the limit, say it is 0 and this is an arbitrary angle, let's say this is theta dot, then the angular velocity is theta dot. So we have here, this will be theta dot d theta dot, and this one will be 27.67, this is minus, we have cos theta. Oh, sorry, we need to integrate, show this integration. So it should be written in this manner, that it will be 27.67 into integration sine theta d theta, and the limit of integration is from 0 to, this is any limit, any angle theta. So we can say from here, this is turning out to be as theta dot square by 2, and this one will become 20, this is minus 27.67, it is minus cos theta, so it will be cos theta minus cos 0 means 1. So this minus sign can be absorbed and can be written from here that theta dot square will be equal to 2 into 27.67. So we can take this 2 multiplied by 27.67 will yield the value 55.34. So we take, this is 55.34 into 1 minus cos theta. Now we see that this is the theta dot square for any arbitrary angle theta, correct? But we know that if it is to lose contact at point A, then theta dot square must be equal to 6 by 5 cos theta, means it is 1.2 cos theta. So I can therefore say that if we can make this, equate these two, and can write from here that it means these two are basically giving the same thing. So I write therefore that 1.2 cos theta then must be equal to 55.34 minus, it is 55.34 cos theta. So from here we should be able to get that cos theta should be equal to 55.34 divided by, it is 55.34 plus 1.2. So it therefore gives me the value of theta, that is, we can say that this value of theta turns out to be as, this is 55.34, to it we can add 1.2, take its reciprocal, multiply it by 55.34 and take the inverse cos, and this turns out to be as 11.83 degree. So the value turns out to be as 11.83 degree. But what does it say? It says that, if we go back to this problem, we see that if the bottom face of the block is notched so that it cannot slip, find the angle theta at which the contact between the block and the corner ceases. So the contact between the block and the corner will cease when this normal reaction, of course, will be equal to 0. That means this normal reaction will be equal to 0. And under such circumstances, we notice from here that the value of theta dot, that is, value of theta, that turns out to be as 11.83 degree. So we see therefore that, students, we therefore discuss the situation of a rigid body which is rotating about a fixed point, and undergoing a fixed axis, rotating about a fixed axis, and we see that how we can apply these equations in our situations to analyze for the kinetics. I hope that with these two examples you have understood the basic concepts of writing or analyzing the kinetics for rotation of a rigid body about a fixed axis, and I will advise you to solve few problems from the book of Merriam and Craig to get further insight into this concept. So we stop here today, and I once again thank you for watching the video.